Warning: this material has been copied or communicated to you by or on behalf of the University of Western Sydney pursuant to Part VA or VB of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further copying or communication of this material by you may be subject of copyright protection under the Act.
Okay, let's begin. We're talking about power series. We want to get through this, guys. Thank you. Okay, we want to get through this fairly quickly, but we're talking about power series. This is a power series about x equals 0. You've seen it written out here in full. But you also need to get used to the sigma notation. Okay, so what this sigma notation is saying is add sum, sigma, s for sum, with n going from 0 to infinity, so n is for a0 x to the 0, and in this case, whether x is 0 or not, we do take that to be 1. So that's a0 times 1, that's that first term. When n is 1, we have a1 x to the 1, that's the second term, etc. So that just builds up like that. Now, listen carefully. When you first learnt about powers and things, and you know what 7 to the power 3 times 7 to the power 5 was, it was sort of almost easier to write 7 times 7 times 7, that's 3 of them, and then another 7, 7, 7, 7, 5 of them, and then sort of look them all and say there's 8 of them. But you pretty soon learn that rather than writing that out in full, it's easier to just learn an extra little rule about adding powers, especially when you're wanting to do 7 to the power 100 times 7 to the power 200. Okay? So sigma notation initially looks a little bit complicated, and there are a few extra little rules to learn about it, but ultimately it's a much neater notation. You won't be required to learn the sigma notation here, but if you're thinking of going on and doing some extra maths, or if you like maths, then it's worth having a look at and trying to come to terms with it a little bit. Okay, so this is a power series about x equals 0, and remember I said that the radius of convergence goes out to a certain point. But if you need the function at a different point, you can actually have, instead of having to have it about the origin, you can have it at some other point. And basically all it does is, instead of having an x there, you have x minus whatever that middle point is there. And so you see, even when c is 0, you get x minus 0, which goes back to this form here. So all that is instead of the powers being x, they're powers of x minus whatever that centre of your power series is that you want. Okay? Now, a power series about, if I give you any function, how might we find these sort of power series? Where did these come from? Well, they're actually things called Maclaurin series, and there's a formula for them that looks like this. And if you think of what that means, it really is, if you take n as 0, that means the 0th derivative. It's f of 0 plus the first derivative evaluated at 0 over 1 factorial x plus the second derivative evaluated at 0 over 2 factorial x squared, etc. And that pattern just keeps going. Now, as an exercise, try that for e to the x, for cos x and for sin x, and see if you can get those power series out of that formula. All right? So that's an exercise for you to try to get those. The first one's pretty easy, because if we have an exponential function, e to the 0 is 1, and the derivative of e to the x, and e to the 0 is, and the second derivative of e to the x, and e to the 0 is. So they're all 1s, aren't they? And if you put 1s all the way through there, that's exactly the power series you get, dividing by the bigger and bigger factorials. Your task then is to really have a look at cos and sine. Okay, now this morning, when I was showing you the graphs and talking about radius of convergence and that sort of thing, that's basically what we're talking about in this little section here. And if I tell you that a function is analytic, that basically means it has a power series. Okay, so if I tell you a function, now, and you might think that, well, don't all functions have power series? No, first of all, if they don't even exist at 0, they don't have a power series at 0. So, for instance, the log function doesn't have a power series about x equals 0, because you can't even put the 0 in there. But there are also some power series. Instead of dividing by the factorials, if I said 1 plus 1 factorial x plus 2 factorial x squared plus 3 factorial x cubed plus etc. Okay? Just like here, if you're dividing by the factorials, it doesn't matter how big you make x, it will always converge to an ordinary number. Here, it doesn't matter how small you make x. Because the factorials get big so quickly, even if x was a million millionth, and then you'd have a million millionth cubed and whatever, that's pretty small, they're pretty small numbers. But because you're eventually multiplying by factorials which are bigger than powers, it doesn't matter how small that number is in there, that will always end up getting bigger and bigger and bigger and going off to infinity. So the only number that you can put in there that makes sense for is x equals 0, because then that's just 1. But we're not really interested in a power series that is 1 when x is 0 and infinity for everything else. Okay, so that's not a very good power series. How do we tell the difference? Well, we say that doesn't actually converge for anything outside 0. So the radius of convergence of that is 0, but we don't want that. We want radiuses of convergence, or radii of convergences bigger than 0. So if I tell you a function is analytic, that basically means to you it's got a decent power series. It's got a power series that isn't just a silly one like this that only has one value and diverges for everything else. Okay? So it basically means you've got a decent power series. Now what we would like to do is apply that to, for instance, a linear second order ODE, where these may be functions of x, and not just the Euler-Cauchy type functions of x or constants, and a right-hand side. It turns out that it's worth looking for power series solutions if each of these functions of x are analytic, that is, if they each have reasonable power series. So if these things have reasonable power series, then you can expect y itself to have a reasonable power series. So that's one thing. On the other hand, if they don't have reasonable power series, you still may sometimes be able to get a power series for y, although not often. But in some special cases, for instance, in the Euler-Cauchy case, the Euler-Cauchy case, remember, says this polynomial is a over x and this polynomial is b over x squared. It turns out that there's at least one power series, usually, sometimes, in the Euler-Cauchy case, even though these don't actually have power series. How do I know those functions don't have power series about x equals 0? Because I can't even put x equals 0 into those things. Okay? All right. So there are just a few other easy power series. What if I had a polynomial? What if I had x squared plus 2x plus 1? Does that have a power series? Well, let's think about it. If I were to try to put it in a form up here, well, the a0 would be 1, the a1 would be 2, the a2 would be a 1, and what would a3 then be? How many x cubes are there down here? None. So a3 would be 0. And what would all of the later coefficients be? Is 0 an okay number? Yeah. So this actually is its own power series. You see, any polynomial can be written as this with zeros for all of the higher and higher and higher power series terms. So that's actually easy. These things are a little bit harder to figure out, but if you've got a polynomial, so a constant has a power series because it's just 1 plus 0 everything else. A linear function is its own power series. Any polynomial is its own power series. Okay, let's look at this case here. That's the p function, that's the q function, that's the r function. So, does this have a power series? Yeah, it's its own power series. This is the power series x squared, so that means that would be a 0, that would be a 0, that would be a 1, and then everything else would be 0. What about x minus 1? Does that have a power series? Well, yes, that would be a minus 1, that would be a 1, and then everything else would be 0. So yeah, that's okay. What about 0? Does 0 have a power series? With all zeros. Okay, so that's a pretty trivial one. But yeah, so 0 itself is a power series. So in fact, r of x equals 0, and they're all okay as power series. So in fact, all are analytic. And so we would expect to be able to get, I haven't said how yet, but we'd expect to be able to get power series solutions for that ODE, even though we can't solve it at the moment because it's not constant coefficient and it's not Euler-Cauchy because the powers don't match the derivative. Okay, so we should at least be able to get a power series which we can approximate. If we take the first 10 terms of the power series, that will give us an approximate solution. What about this case, however? Well, it looks like those things have power series, but that's not what the theorem says. The theorem says you have to have it in standard linear form. So we have to divide through by the x first of all, which would mean that the p function would be x squared over x, which is x, so that one's okay. X is its own power series. And the q is a 1 over x. So the answer to the question, and obviously the r is 0 as well, the answer to the question as to whether it would be worth looking for power series for this is we don't know. It might be one of these special cases where there's still a power series, but we don't know. Okay, so this theorem tells us if these functions here are analytic, that is, if they have decent power series, then we will definitely be able to get a power series solution. But if they don't have decent power series, we might not. All right, so that's the idea. Let's have a look at how we might do one of these power series. So here is a second order. It's not constant coefficient and it's not Euler-Cauchy. So let's try the power series. The p function, that is the function in front of the derivative, is a 0. So yes, that's analytic. It's its own power series. The q function is minus 2x. That's a polynomial, so that's okay. The r function is 0, so that's okay. They all have power. So we do expect a power series solution. So instead of both, all are analytic at x equals 0. So there's a power series. Well, let's write that out. Just concentrate on this side first. Forget the sigma notation at this stage. You can see that that's the power series. That's what we've written it out. It's a constant. I want to do a bit more. Okay, so there they are. Constant times x squared, etc. That's what it looks like, but just ignore that for the moment. We would like to be able to substitute a second derivative, but for a second derivative we need a first derivative. So let's differentiate this. Derivative of constant, 0. Derivative of a constant times x, just the constant. But look, I'm keeping everything in the columns. I'm having a constant column, an x column, an x squared column. Sorry? What do you want? Sorry? Do we need focus or? Bit better? Is that right? Yeah, okay. All right, so that's where that comes from. Derivative of a constant x squared is 2 times the constant x, so that's where that one comes from, etc. But I'm keeping everything in their right columns. So, second derivative, well, derivative of constant is 0. Derivative of constant times x is the constant, so that's come from there. This derivative will be 6a3, so it's come from there, 12a4, etc. And these ones have come from what we imagine are going to be in the later terms out here. Anyway, but you will get so used to writing these out that these will just be straightforward. Okay, so this is what we need. Now we need to build this up. Well, we have a second derivative. There it is there. We need to subtract off 2x lots of y. So we need to subtract off 2x lots of this thing. So what's minus 2x lots of a naught is minus 2x a naught. But we'd put this in the x column. So there it is there, minus 2x. So this much here is the ODE that we're building up. The minus 2x, there aren't any constant terms. This times this gives me that term. Then this will be an x squared and this will be an x cubed, etc. Okay? Now the right-hand side of the ODE is 0. It could be something else. It could be non-homogeneous, but 0 as a power series is 0 plus 0x plus 0x squared, whatever. If it was something else, we'd write out whatever the power series for that something else would be there. All right? And now the only way that this can be true for all values of x is if each of these coefficients of x match up. So the 2a2 must be 0. And then the 6a3 minus a0, 2a0 must be 0. And the 12a4 minus 2a1 must be 0. And if these were other things, because this was a power series of a different function, then they would still have to match up to whatever those coefficients are. Okay? Now, the rule here is to solve the later coefficient in terms of the earlier. So A3 is the later, A0 is the earlier. So we've solved A3 in terms of A0. This one, A4 in terms of A1. If we get down to the next one, 20A5, that's this thing here, in terms of A2, but you see we already know something about A2, so we can jump back and use what we've learnt previously about A2, and that means that A5 turns out to be A2 divided by 10, but then it's 0 once we put that in. We could even, just by following the pattern, write out what the next one is. So you can see that this is 2 times 1, 3 times 2, 4 times 3, 5 times 4. So this is the next one, just following the pattern, is going to be, instead of 5 times 4, it's going to be 6 times 5. So 30, 2, 3, 4, 5, A6, minus 2, A0, A1, A2, A3 equals 0 will be the next equation along there. So we could solve that also. We could say that A6 subtract divide by 30 is going to be A3 over 15, but we also know something about A3. A3 was 1/3 of A0, so that's A0 over 45. Okay, so actually what's going to happen is we got down to this stage. A5 went back to something to do with A0. A6 went back to something to do with 0. A6 went back to do with something with A0. What do you think A7 is going to go back and have something to do with? A1. And then A8 will go back to A5, but A5 was 0. And A9 will go back to A6, but A6 went back to A3, so everything, in fact, will either go back to 0 or eventually through enough steps to A1 or A2. So how many unknown coefficients will there be that we end up with after doing all of this? Well, we know what 0 is, and then there's only A0 and A1 left over. Okay, everything else is known. Comes back to A0 and A1. But then, hang on, a general solution to an ordinary differential equation should have how many unknowns if it's second order? 2. And you see that's come out here, sort of almost magically. It's come out and everything works back to the only things we don't know are A0 and A1. And they are the 2 arbitrary coefficients of the general solution. Well, how do we use all of those? That's just the form of the power series before we knew anything about it. We still don't know anything about A0. We still don't know anything about A1. We know that A2 is 0, so there's no x squared term. We know that A3, looking back up here, is 1/3 of A0, so there it is there. A4 is 1/6 of A1, so there it is there. And then further on. So in fact, everything just has to do, we could even take common factor of A0 out there if we looked at every second term. So there's going to be a 1 from there, 1/3 from there, and there'll be something else later on. A1 outside of x and x to the 4th, etc. So you see, this even looks like C1y1 plus C2y2. That's the form of the general solution. Okay, it's some constant times a function of x and another constant times a function of x. And sometimes you might even be able to recognise what those functions were back in terms of the original function before it was a power series. So you might even get to a stage where you could say, well, I know that looks like either the x or cos x or something like that, and even replace them like that. Okay? But then, you see, this could be used as an approximation. Even if you can't do that, you could say, okay, well, I know that for the values of x that I'm interested in, this function will give me a good enough approximation as long as I take up to powers of 10 or something else, something like that. Okay? So then I can use that as an approximation. Now, just to look at this quickly, if we did want to use sigma notation, which, yes, initially is a little more complicated, but ultimately, for those of you that want to go on and use some mathematics, is a better way of doing things if you learn a few little rules. These are the little rules. Well, first of all, we need to understand what it is. So this just means substitute n as 0 and add n as 1 and add n as 2 and 3. So when you look at that, you just think, okay, it's something x to the 0, something x to the 1, something x to the 2, all added together. So you've got that in your mind. Now, if I were to differentiate this, I had to do 1, 2, 3, 4, 5 derivatives to get this. How would I differentiate this? Well, I know how to differentiate x to the n. It's bring the n down, subtract 1 from the power. Okay, that's very easy. That was just one differentiation instead of 5. But there is the one slight rule. You have to look at what the constant was here. The constant term was with n equals 0. And you see now that this starts with n as 1 because the constant term differentiated away to be 0. So that's the one complication. When you do the derivative, you've got to have a think about what happens to the constant term here. And that means that this sigma sign starts at n equals 1. If it started at n equals 0, you'd have a term that wasn't useful in there. Well, second derivative would be another 5 differentiations, but how would I differentiate this? I would just bring the power down, there it is there, subtract 1 from the power, and deal with a constant term. So instead of starting at n as 1, I started as n as 2. So that was actually much easier than doing the 5 differentiations. Multiplying the original function y by minus 2x meant a number of multiplications here. Well, all I would do here is put a minus 2 outside. Because it's a sum, a minus 2 outside a bracket really means minus 2 times everything in the bracket. And so I could move that inside. Well, in fact, I could leave the minus 2 outside, but I could move the x inside. And what does multiplying x to the n by another x do? Simply adds 1 to the power. Okay? So you see that, yes, a little complicated if you're frightened by the sigma signs, but it takes, ultimately, it's a much more compact, neater and efficient notation. All right? I won't go through this. See, this is how you would use, what we did here was to find a whole lot of equations. If you wanted to say what a to the 100 was, you'd have to work your way down to 100. Or you could sort of follow the pattern, but that would still be a guess. That wouldn't actually be a proof that that pattern was true. This is how you would prove the pattern. But what I'm going to ask that you do, those of you that are interested in, to read and enjoy. And if you have any questions about this section, then certainly ask me or ask Lynn. We're more than happy to take you through it in a little bit more detail. But once again, it looks really intense, but once you start to get into it and get used to using it, it's a very efficient and useful type of notation. But what you end up with out of that, and another reason that you would do this, is you end up with what's called a recurrence relationship. This is true for any value of k, and so this is the proof of all of these formulae. And if I wanted to know what A100 was, I'd put k as 98, and that would tell me the formula that A100 is 2 lots of A97, because I'm putting, this is A plus 2 in terms of k minus 1. And you see there's a difference of 3 there, and that's really what happened here. There was always a difference of 3. We went from 0 to 3, 4 to 1, 5 to 2. There was a difference of 3 in those coefficients. And that's what's happening. And this just tells you how to get the early one. But then that would mean that if you got from 100 to 97, you could use that to say 97 in terms of 94. And then you could say 94 in terms of 91. And you could work your way all the way back down to where we ended up just with an A1 and an A0. Okay, but I'm going to let you look at that yourself, those of you that are interested. I have given you the extra detail down here if you also want to have a look at it, but when you're doing them in tests and that sort of thing, you only need to do this. Let's look at this case. Second derivative, we need a power series. Well, first of all, is it worth doing it? Well, we look at the P function and the Q function and the R function. They're all just polynomials, so yes, we would expect to have a power series solution. So there is the power series. We'll need a first derivative, second derivative. Well, you've seen those before, haven't you? Okay, we already have that. That's fine. So that's what we have already. I will need an x squared times this. Now, what will multiplying this by x squared? Effectively, it will mean it will just shift it along 2 columns. If we're keeping, again, we've got a constant column and an x column and an x squared column, x cubed column. Okay, this much now is building up the ODE. Okay. There we are. So multiplying this by x squared just effectively shifts everything along to the x squared column. Multiplying y by x just shifts it along here. And what's the power series for 0? Well, it's just this. If I had, if this right-hand side had been e to the x, then if it had been e to the x, I would have written e to the x equals 1 plus 1x plus a half x squared, etc. And then the equations that I get out of this, instead of being equal to 0 in each case, this one would have been equal to 1, this one would have been equal to 1, this one would have been equal to half. Okay? So we're saying that all of these things give us 0, all of those things give us 0, all of those things give us 0, all of those things give us 0. Okay? Equating coefficients. Now those first three lines, you have those already somewhere else, you know, earlier on in the previous example. So I'll just go up to there. So you've got that much. Equating the coefficients. Well, this first coefficient, 2a2 equal to 0, gives me a2 is equal to 0. The next one is 6a3 plus a0 must be equal to 0. 6a3 must be 0. And the rule, remember, solve the later one in terms of the earlier one. So that's subtracting and dividing by 1/6, etc. Does everybody have this much on this page? You'll have this on the on views if you want to go back and read it. You don't have to copy this part down. Just make sure you've got this left-hand side down. And the rest of the coefficients look like that. And if you're interested, you could try the sigma notation at home. So you can see what's happening. We're looking at each of the coefficients, making them equal to 0, solving later in terms earlier. And then if I get back to something that I know about already, I can see that I have an A2 and I know that A2 is 0, then I can use that as well. Then it's a matter of substituting it in and collecting common factors so that you can see it's in that form of a constant times one function of x plus a constant times another function of x. Okay, now if you finish that, have a look at the next one. Don't write the first three lines out again. Those first three lines are going to be the same for all of the problems we do. This is the... So don't write this out again. You've got this in your previous one. Okay? Except, well, now think about what this is going to be. The best way actually to do this would be to think of it as x y double dashed minus y double dashed plus y dashed equals 0, because then we'll be able to have a line for each of those terms. Again, don't write out the sigma notation. You'll see that in views. Don't write these three lines out because you've got them in this previous example that we just did. But what do we need? Well, we need an x times the second derivative. So the first thing that you can write under there, keeping the columns the same, will be this line, x, leave a space because there's no constant, and x times the second derivative that we had there are these things. And we'll need a minus y double dash, so that's exactly the same as y double dashed, which we had back here, except all of the signs have been made negative. And we'll need a y dashed. Well, I can see the y dashed there, so we'd write that again underneath. So all you need to be doing is writing these three lines out here. And that's all supposed to, if you look back up here, be equal to 0. So what's 0 as a power series? It's just the easiest power series there ever is, just zeros all the way along. And we built the DE up. Now, in your working, if you write these things out, it's actually a good idea to bracket the part that's the DE, so that when you come to look at what the equations are, you're reminding yourself that I'm only doing here, I'm not including any of these ones further up. Okay? So have a look. What's the constant term? Then there's the power of x's, then there's the x squareds and the x cubes all the way through, because we've cleverly kept them in their correct columns. And so this is telling me that minus a2 plus a1 must be equal to 0. And so that's that first equation, which we then solve for later in terms of earlier coefficients. This second equation tells me 2a2 minus 6a3 plus 2a2. So altogether that's 4a2 minus 6a3 is equal to 0, which we can solve to get this. But this actually, we know something about a2. It's back here. All right. So the step that went in there was 2/3. Now what was a2? a2 was a1 over 2. And you see those two cancel, which is where we get the a1 over 3. And this is a case, it doesn't step back by 2 or 3 terms, it steps back just to the earlier term. So ultimately, as we work through each of these things, you see that everything comes back to a1. So we know all of the later coefficients in terms of a1. And then ultimately, what don't we know? Well, we still don't know anything about a0, and we don't know anything about a1, so we still have 2 arbitrary coefficients, which is exactly what we need for the general solution. And so substituting those in, term by term, still gives me 2 arbitrary coefficients, only basically what it's saying is that one of your functions is a constant, the other is a constant times this. And it actually makes sense, because if you go back and you look at the DE, it only has a first derivative and a second derivative on the left-hand side. And the derivative of the first, clearly doing maths, the derivative of a constant is 0. Okay? So that's why this comes out as a solution. I think that you have in your notes the sigma notation version fully there, so those of you that are interested can work that through and see how it is that works out. Any questions? It's not too hard. This again, really, to solve this DE, there's hardly any calculus in it. In fact, there's basically none except for the initial differentiation. The rest of it is just putting it all together in some sort of consistent way. Okay. Yep. Where? Further up? There, because the right-hand side is 0. Okay, so that's that term. Then there's the minus y double dashed. Then there's the y dashed, and they're all equal. This is equal to the right-hand side, which is 0. And 0 as a power series is no constant, no x squared, etc. Yeah? Okay, so that's where we're up to. And then you have in your notes how to do it using sigma notation, which you can work through at your leisure. So that's in the notes. And then finally we have an example of how to use a power series if the right-hand side isn't 0. So this is the non-homogeneous case. And if you haven't quite got all of this, it'll be on views anyway for you to go back and check that you've got the right thing. So let's look at this example. Not constant coefficient, not Euler-Cauchy, is homogeneous, is non-homogeneous. Okay? So we do the same thing. Don't have to write that out. You've got this in front of you anyway, but well, for your own, when you were doing this yourself, you would write this out once, but then doing later problems, you just refer back to this. And we now want to build up second derivative, first derivative times x, and a 1. So we can use the second derivative that we've just written out. What does x times this do? Well, it simply shifts. Instead of a0, it makes it a0x, which shifts it along a column. And it makes this a1x squared, which shifts it along a column, etc. And then the right-hand side is 1. You see, this much is the dE. It's that plus that equals that. Yeah? But what's 1 as a power series? Because this side is power series. Well, it's 1 plus 0x plus 0x squared, etc. All right? So in this case, instead of 2a2 being equal to 0, as it has been in the past, it's now equal to 1. And so that means that a2 is a half. And then we can keep doing the same thing as we've done before. 6a3 plus a0 must be 0. 12a4 plus a1 must be 0. Solve for later coefficient in terms of earlier coefficient. Do I know anything about a0 at the moment? No. Do I know anything about a1 at the moment? No. Do I know anything about a2? Yes. It was a half. So minus 1/20th times a half is minus 1/40th. The alternative is to do that in sigma notation, but ultimately you come down to, well, we'll look at it this way. Y is a0 plus a1x plus a2x squared plus etc. So plugging these things in gives me, don't know anything about a0, don't know anything about a1. I know that a2 is a half. I know that a3 is minus a0 over 6 x cubed. I know a4 is minus a1 over 12 x to the 4th. I know that a5 is minus 1/40th x to the 5, and that goes on forever and ever and ever. Now, at sigma notation, so you see how I put that in. Well, that's exactly what we've written down here, but we can also pull out the common factors. So there's an a0 there, an a0 there. There'll be an a0 further on, but there's at least the two of them, the 1 and the minus x cubed on 6, and that will keep on going forever and ever because there'll be lots more a0s further out here. A1 there, A1 there are those two terms. And then there's these other terms that don't have a0s or a1s in them that end up being these terms out here. Now, what does that look like? What does that look like? That looks like the same sort of form as we've seen for the non-homogeneous case, where we found that the function was sum of a homogeneous solution and a particular solution. The homogeneous was the one with the unknown constants, and this was the particular solution. Now, it's not necessarily true that this is the homogeneous solution, okay? All I'm saying is it looks like the same form. The reason that it's not necessarily the homogeneous solution is that there could be bits and pieces of constants that have been taken out of here that could have been taken out of there and added up and made things slightly different. But it still looks the same. It's something that has the arbitrary constants and something that is just a function. Okay, well done. That's power series, and you owe me 6 or 7 hours at least. If you're an average student, more if you're not an average student over the next week, plus the hours from the previous weeks that you might not have put in. See you next week. Remember pass and remember your tutes. Your tutes are a good way to use some of the time you owe me. The lecture is on the web. Yep.
Question.
Good.
One of the questions I couldn't do. You know how you equate coefficients?
Just come up here.
Okay.
Sorry.
No worries.